The use of copper sulfate to lower ground rod resistance is not a recommended practice. There are several reasons why this method should be avoided, primarily due to its potential for creating corrosive conditions and its questionable long-term effectiveness. Ground rods are installed to provide a path for fault current to return to the source, thereby tripping a circuit breaker or fuse and clearing the fault. A low resistance ground is desirable to facilitate this process. However, using copper sulfate to achieve this low resistance introduces a number of problems. Firstly, copper sulfate is a highly corrosive chemical. When mixed with the soil and watered down, it creates an electrolytic solution that can accelerate the corrosion of the ground rod itself, as well as other buried metallic objects in the vicinity, such as underground pipes, metallic conduits, and other grounding electrodes. This corrosion can weaken the ground rod, reducing its effectiveness over time and potentially leading to a complete failure of the grounding system. Secondly, the effectiveness of copper sulfate in lowering ground resistance is often temporary. The copper sulfate solution tends to leach away over time, especially in areas with high rainfall or fluctuating water tables. As the copper sulfate dissipates, the ground resistance gradually increases, negating any initial improvement. This means that the grounding system would require periodic reapplication of copper sulfate to maintain its low resistance, which is not a practical or sustainable solution. Thirdly, the use of copper sulfate can have detrimental environmental effects. Copper sulfate is toxic to many organisms, and its presence in the soil can contaminate groundwater and harm plant life. The runoff from treated areas can also pollute nearby streams and rivers, posing a risk to aquatic ecosystems. For these reasons, electrical codes and standards generally discourage or prohibit the use of copper sulfate to lower ground rod resistance. Instead, there are several alternative methods that are considered to be more effective, reliable, and environmentally friendly. One alternative method involves using multiple ground rods. Connecting multiple ground rods in parallel can significantly reduce the overall ground resistance. The National Electrical Code, or NEC, specifies requirements for the number and spacing of ground rods. Typically, 2 or more ground rods are installed at least 6 feet apart. The resistance of multiple ground rods in parallel is generally lower than that of a single ground rod. 2. Improving soil conductivity around the ground rod is another method. This can be achieved by replacing the existing soil with a more conductive material, such as bentonite clay or a specialized grounding compound. These materials have a high water retention capacity and create a low resistance contact between the ground rod and the surrounding soil. These compounds are specifically designed for grounding applications and are non-corrosive and environmentally safe. 3. Using a larger ground rod can also reduce resistance. A longer ground rod will make more contact with the earth and improve the electrical connection. Ground rods are typically available in lengths ranging from 8 feet to 10 feet or more. The NEC specifies minimum requirements for the size and type of ground rods depending on the application. 4. In some cases, it may be necessary to use a ground plate or a ground grid. A ground plate is a large metal plate that is buried in the earth to provide a large surface area for grounding. A ground grid is a network of interconnected conductors that is buried in the earth to provide a low-resistance grounding path. Ground plates and ground grids are typically used in applications where very low ground resistance is required, such as at electrical substations or telecommunications facilities. 5. Another alternative is to use a chemical ground rod. Chemical ground rods contain a chemical compound that leaches into the surrounding soil, creating a conductive zone around the rod. These rods are designed to provide a long-lasting, low-resistance ground connection. However, it is important to select a chemical ground rod that is environmentally safe and complies with local regulations. 6. Proper installation techniques are crucial for ensuring a low-resistance ground connection. The ground rod should be driven vertically into the earth to its full length. If the soil is too rocky or hard, a pilot hole may be drilled to facilitate installation. The connection between the ground rod and the grounding conductor should be made using a listed connector that is suitable for direct burial. 7. Regular testing of the grounding system is important to ensure that it remains effective over time. Ground resistance should be measured periodically using a ground resistance tester. If the ground resistance is found to be too high, corrective action should be taken to lower it. 8. It's also important to consider the local soil conditions. Soil resistivity can vary significantly depending on the type of soil, moisture content, and temperature. In areas with high soil resistivity, it may be necessary to use more extensive grounding measures to achieve a low resistance ground connection. 9. The NEC provides detailed requirements for grounding and bonding in electrical systems. These requirements are designed to ensure the safety of people and property. It is important to consult the NEC and other applicable standards when designing and installing a grounding system. 10. It is always advisable to consult with a qualified electrician or grounding specialist to determine the best grounding solution for a particular application. A qualified professional can assess the site conditions, evaluate the electrical system requirements, and recommend the most appropriate grounding methods. In summary, using copper sulfate to lower ground rod resistance is not a recommended practice due to its corrosive effects, temporary effectiveness, and potential environmental hazards. There are several alternative methods that are more effective, reliable, and environmentally friendly. These methods include using multiple ground rods, improving soil conductivity, using a larger ground rod, using a ground plate or ground grid, using a chemical ground rod, proper installation techniques, regular testing considering local soil conditions, and consulting with a qualified electrician. Always follow the requirements of the NEC and other applicable standards when designing and installing a grounding system. This will help to ensure the safety of people and property and provide a reliable grounding connection for the electrical system. Furthermore, it's crucial to understand the importance of a properly grounded electrical system. Grounding serves several vital functions. Firstly, it provides a low impedance path for fault currents, allowing protective devices such as circuit breakers and fuses to quickly clear the fault and prevent electrical shock hazards and equipment damage. Secondly, grounding helps to stabilize voltage to ground, reducing the risk of voltage surges and transient overvoltages that can damage sensitive electronic equipment. Thirdly, grounding minimizes electrical noise and interference, improving the performance of electronic systems. Fourthly, grounding provides a reference point for electrical measurements, ensuring accurate readings. A properly grounded electrical system is essential for the safe and reliable operation of electrical equipment and systems. Grounding electrodes are an integral part of the grounding system. They provide a physical connection to the earth, allowing fault currents to flow back to the source and tripping protective devices. Grounding electrodes can take various forms, including ground rods, ground plates, ground grids, and metal water pipes. The NEC specifies requirements for the type, size, and installation of grounding electrodes. Grounding conductors connect the grounding electrodes to the electrical system. They provide a low impedance path for fault currents to flow back to the source. Grounding conductors must be properly sized and installed to ensure that they can safely carry the maximum fault current. Bonding is another important aspect of grounding. Bonding involves connecting together all metallic parts of an electrical system, such as metal conduits, metal enclosures, and metal equipment frames. Bonding creates a low impedance path for fault currents, minimizing voltage differences between different metallic parts and reducing the risk of electrical shock. The NEC provides detailed requirements for bonding in electrical systems. Ground fault circuit interrupters, or GFCIs, are another important safety device that is used in conjunction with grounding. GFCIs are designed to detect ground faults and quickly interrupt the circuit, preventing electrical shock hazards. GFCIs are typically installed in areas where there is a high risk of electrical shock, such as bathrooms, kitchens, and outdoor locations. Surge protective devices, or SPDs, are used to protect electrical equipment from voltage surges and transient overvoltages. SPD diverts surge current to ground, preventing it from damaging sensitive electronic equipment. SPD are typically installed at the service entrance of a building or at individual pieces of equipment. Regular inspection and testing of the grounding system is essential to ensure that it remains effective over time. Ground resistance should be measured periodically to verify that it is within acceptable limits. Bonding connections should be inspected to ensure that they are tight and corrosion-free. GFCIs should be tested monthly to verify that they are functioning properly. SPD should be inspected periodically to ensure that they are in good condition. Any problems with the grounding system should be corrected promptly to ensure the safety of people and property. In addition to the technical aspects of grounding, it is also important to consider the legal and regulatory requirements. Electrical codes and standards, such as the NEC, specify minimum requirements for grounding. These requirements are designed to protect people and property from electrical hazards. It is important to comply with all applicable codes and standards when designing and installing a grounding system. Local regulations may also impose additional requirements for grounding. It is important to check with the local authorities to determine what regulations apply in a particular area. Failure to comply with applicable codes and regulations can result in fines, penalties, and legal liability. Proper grounding is essential for electrical safety. It protects people from electrical shock, prevents equipment damage, and minimizes electrical noise and interference. By following the recommendations of the NEC and other applicable standards, and by consulting with a qualified electrician or grounding specialist, it is possible to design and install a grounding system that will provide reliable protection for people and property. Remember, when dealing with electrical systems, safety is paramount. Always take precautions to avoid electrical shock hazards. If you are not qualified to work on electrical equipment, consult with a qualified electrician. Electrical work can be dangerous, and it is important to have the proper training and experience to do it safely.